Today we are going to discuss elements of Earth's magnetism. What are elements of Earth's magnetism? What are the different types of those elements? How we define them? And then what are the details of those elements of Earth's magnetism? What other information we can get from these elements of Earth's magnetism? Then what is their importance? How they are represented? And above all, we'll discuss why we have only 3 elements of Earth's magnetism. What is their importance? So all these we'll discuss in today's discussion. Elements of Earth's magnetism are 3 in number. First one is declination, which we normally represent with theta. Next is angle of dip, which we represent as delta. And third one is horizontal component of Earth's magnetic field, which is usually represented by dH. Let's now try to see what does these terms stand for and what is their importance. Let's see what does declination at a place means. Declination at a place is the angle between geographic meridian and magnetic meridian at that place. So at any particular place, the angle between the geographic meridian and magnetic meridian will be the declination at that place. Now, what is geographic meridian or magnetic meridian? Geographic meridian is the vertical plane passing through geographic north and south pole. If you take Earth and its north and south poles are there, so the vertical plane which will pass through the geographic north and south pole, that will be called as the geographic meridian. And for magnetic meridian, this is the vertical plane passing through the poles of a freely suspended magnet at that place. Suppose I take a particular place where we want to find declination, and for that we need magnetic meridian. Now, if you have a freely suspended magnet, the vertical plane which will pass through the poles of a freely suspended magnet, that will be called as the magnetic meridian at that place. In fact, this is the vertical plane passing through magnetic poles at that place. So the angle between geographic meridian and magnetic meridian, that will be called as the declination. Like suppose if you have this being represented as geographic meridian. So this is suppose the geographic meridian. And we have suppose this one being represented as the magnetic meridian. This is the vertical plane passing through the poles of a freely suspended magnet. So this is the magnetic meridian. So the angle between these two, this particular angle is the declination. So this angle theta is the angle between geographic meridian and magnetic meridian at that place. So this particular angle is your declination at that particular place. Next term is angle of dip. It is the angle through which the north pole of a freely suspended magnet dips with the horizontal at that place. Now, what does it mean? Suppose you have a freely suspended magnet and this represents the north pole, this is the south pole. So if at a particular place, the freely suspended magnet has its north pole dipping with some angle with the horizontal. So the angle through which it will dip with the horizontal, that particular angle, we call it as the angle of dip. Similarly, you can define it in other words like it is the angle made by the Earth's magnetic field at a place with the horizontal direction. Like suppose here we take a freely suspended magnet and suppose this one is inclined like this. That means this is the north pole, this is the south pole of that. It is dipping with the horizontal there. So this particular angle through which it is dipping with the horizontal, this is the horizontal direction. So this particular angle will be called as the angle of dip. In fact, if you consider Earth's magnetic field at that place, so that one will also be in this direction. So this is suppose the Earth's magnetic field at that place. So this particular magnetic field and this is the horizontal direction. So the angle between the two that will be called as the angle of dip. Let's assume that we are there at the equator, and now if we have a freely suspended magnet, in that case it will remain horizontal because both the poles of this freely suspended magnet will be equally pulled by the Earth's magnetic poles. I mean, if we start moving towards in the northern hemisphere or in the southern hemisphere, now we are approaching more close to the magnetic pole inside Earth, or the magnetic pole, which is the cause of the Earth's magnetic field. So in that case, the poles of this freely suspended magnet, now they will be unequally pulled. Suppose we are there at the North Pole. So in that case, the imaginary magnet which we assume inside the Earth will have the South Pole there. So now it will be pulling this freely suspended magnet so that the North Pole of this will be pulled more strongly there and it will become vertical. So in that case, this one is now making an angle 90 degrees with the horizontal direction. As a result, at the pole, the angle of dip will be 90 degrees. At the equator, it is 0. And as we are approaching towards the pole from the equator, so as we are approaching it, in that case, we are moving closer and closer to the poles, a magnetic pole inside the Earth. So in that case, this magnet will start dipping. That means it will start getting inclined at some angle with the horizontal. And its extreme position will be, it will become vertical at the pole there. So the angle of dip there will go on changing. So the angle through which it turns with the horizontal or dips with the horizontal, that is called as the angle of dip. And the freely suspended magnet will basically try to align itself in the direction of the net magnetic field at a particular place. So in that case, Earth's magnetic field will also have the same direction, which is indicated by the north and south poles of the freely suspended magnet. So that is why we also say that it is the angle made by the Earth's magnetic field at a place with the horizontal direction. So this is the thing what we get there. But here, just remember one thing. If you consider Earth, this is suppose the Earth there, and this is the north pole of the Earth, this is the south pole. That means this particular direction is the direction of the geographic north and south pole. The imaginary magnet which we assume inside the Earth, which we assume that it is the cause of the Earth's magnetic field, is not exactly in this north-south direction, it is at some angle there. So that imaginary magnet, if you consider, it is inclined like this. The imaginary magnet inside the imaginary magnet inside the Earth will have orientation something like this. That means it is inclined at some angle with the geographic north-south direction. This is the south pole of the imaginary magnet inside the Earth, and this is the north pole. So if it is asked at which particular place the angle of dip is 90, we say that it is at pole. But remember that angle of dip is 90 only at magnetic pole. That means it will be at this particular place and here where it will be 90. It is not at the geographic north and south poles. So it is the magnetic poles there where this particular angle of dip will be 90. So remember that angle of dip is 90 at magnetic poles. Similarly, if you consider the equator there, then in that case its equator orientation will be also like this. That means in normal case we assume like this, and other case it will be inclined like this. So for that also, if it is asked that what is the angle of dip at the equator, it is 0 only along the magnetic equator there. So angle of dip will be is 0 at magnetic equator. So angle of dip is 90 at magnetic poles and it is 0 at magnetic equator. But if suppose in the question it is just asked where angle of dip will be 90 degree there, and it is mentioned with just one option is given there, that it is the poles. So there you can select poles. But in particular question, if both the options are there, it is the geographic poles or magnetic poles, opt for magnetic poles, because only at that particular place there angle of dip will be 90. Similarly, only at magnetic equator angle of dip will be 0. Third element is horizontal component of Earth's magnetic field. It is basically the component of the Earth's magnetic field in the horizontal direction, and this we represent it as BH. Like suppose if we assume that this is the magnetic field of Earth at a particular place. This is the horizontal direction, and this is obviously the vertical direction we are taking. So the angle made by this one with the horizontal direction, we have already said that it is the angle of dip. Now if you resolve this B in the horizontal and the vertical direction, we get the component as BH. This is the component of the Earth's magnetic field in horizontal direction, and by definition we have represented it as the horizontal component of Earth's magnetic field, so that we can write it as BH. Similarly, here we can write this as BV, that is the vertical component of the Earth's magnetic field. So obviously, if you consider now how much we can write for BH, this will be your B cos delta, because it is a component making an angle delta with the net magnetic field. So in that case, BH will be your B cos delta. Similarly, if I want to write the expression for BV, in that case it is your B sin delta. So this is the vertical component of Earth's magnetic field. And if you just combine these two, then what we can get? We can get BV by BH. This is B sin delta by B cos delta, and that is your tan delta. So tan delta is BV by BH. So this is the relation between vertical component and horizontal component of Earth's magnetic field with angle of dip. Because from here we can write delta equals to tan inverse BV by BH. Now, some important conclusions we can draw from this one, that if you consider at poles, at pole the angle of dip is 90. So at pole, if you put there delta, in that case you will get horizontal component at 0. So at poles, that means when we are calling it, that means it is the magnetic poles. So at pole delta is 90. So BH will be equals to B cos pi by 2, and that is 0. And BV, this will be your B sin pi by 2, and that is B. Remember that when we say that at pole we have a freely suspended magnet, it will get aligned in only vertical direction. If it is in the vertical direction, it means Earth's magnetic field is in the vertical direction there. And if it is in the vertical direction, obviously there is no component in the horizontal direction. That is why we get BH equals to 0. And BV, which will be equals to B. Remember that if the magnet is exactly vertical, that is indicating that the net magnetic field is in the vertical direction. So obviously, as it has no horizontal component, whatever magnetic field is there at that particular place, it is only the vertical component. That is why the total magnetic field will also be equal to just the vertical component of Earth's magnetic field at that place. Another case, if you take it at a magnetic equator, in that case the magnet is horizontal there. In that case, the angle made by this with the horizontal direction is 0. So there delta is 0, angle of dip is 0 there at the magnetic equator. So BV, if you consider, it will be your B sine 0, that is 0, and BH will be your B cos 0, that is B. Here again you can see at the equator, magnetic equator, vertical component will be 0 because it is the magnet which is perfectly horizontal there. So if it is horizontal, that means net magnetic field is also in that direction. So obviously there is no question of any vertical component. And at the same time, we can also say whatever is the horizontal component, it is the net magnetic field at that place also. From BH and BV, we can also get one more relation, that if you consider BH square plus BV square, this will be your B cos square delta plus B square sin square delta, and that is your B square cos square delta plus sin square delta, and that is your B square. So BH square plus BV square is your B square. So that means this is another relation between the vertical component, horizontal component, and the Earth's magnetic field at that place. And this we can also write as the BH square plus BV square is square root. This is B. So this relation also we can get. Suppose we have to represent all these elements of Earth's magnetism in a single diagram, then we can show that this PQRS, this one represents the geographic meridian. This is the vertical plane passing through geographic north and south pole of Earth. PQ-R-S, this represents magnetic meridian, because this is the plane in which you have the freely suspended magnet, or the Earth's magnetic field is lying in that plane. So B represents the Earth's magnetic field at that place. So obviously this will be lying in the magnetic meridian. This theta represents the declination. Delta is the angle of dip. And BH, which we have taken as the horizontal component of Earth's magnetic field. So this is the third element. So we have the declination, angle of dip, horizontal component, also the geographic meridian, magnetic meridian, the vertical component of the Earth's magnetic field, all represented in a single diagram. Let's now discuss why we have three elements. Three elements we have taken because these three elements are sufficient parameters which can give complete information about the Earth's magnetic field at a particular place. Or suppose you have a particular point on a line. In that case, we need only one coordinate. If the particular point is there on a plane, we need two coordinates. What is that? If it is in Cartesian system, it is your x and y. If it is in polar coordinate, in that case it is r and theta. And if the particular point is in a space, in that case we need three coordinates, x, y, z. So it is your x, y, z are the three coordinates required to give the complete information about the location of a particular point. And if you take it in polar coordinates, then it is your r, theta, and phi. Here, if you want to give complete information about the Earth's magnetic field at a particular place, in that case, again, we'll need three coordinates there, or three parameters will be there. One will be related with its magnitude, and the two will be related with its orientation. Just like here you have r, theta, and phi. So there also we have your BH, theta, and delta. See, one is the term which is giving the magnitude, like r. And the two angle terms are there. One is your declination and other is your angle of dip. So with that, you can get complete information about the magnitude of the Earth's magnetic field at a place, about its direction, that means how it is oriented, in a plane, how it is oriented, about a particular axis, how it is oriented. So you can get complete information about the Earth's magnetic field at a place. That is why these are called as the elements of Earth's magnetic field.